This is Jack Jackson. Today we're going to talk about arithmetic series. In fact, this is going to be our introduction to what we mean by a series, and we're going to contrast that with a sequence, which is a closely related idea. And we've talked about sequences before, but we're going to talk about series today. That's going to lead us to summation notation, and a related thing that's kind of similar is product notation, so we're going to go ahead and go over that today as well. And then we're going to see if we can find a formula for the sum of a finite arithmetic series. We've looked at arithmetic sequences before. Now we're going to look at an arithmetic series and find its sum. And then we'll look at some exercises and at least one application. So recall that a finite sequence of length n is a function whose domain is the first n natural numbers, or perhaps the first n whole numbers. An infinite sequence is a function whose domain is the set of all natural numbers, or possibly all whole numbers. So sometimes we have a zeroth term, and sometimes we start with the first term. In what we're going to do below, we're going to start with the first term. But a finite series is the number found by adding together the terms, that is the outputs, of a finite sequence. So it's just adding up terms in a sequence. So in a sequence we have these outputs listed out, but in a sum we have pluses between them, and that makes a series. Now, to do this, one notation that we want to introduce is called summation notation. So we're going to use the Greek letter sigma for this. Now, the Greek version of the Roman letter S, standing for sum, is sigma. Now, there's both an uppercase and a lowercase sigma. You can see it there. And we have an upper and lowercase sigma. And we're going to use the capital sigma for the sum. So the symbol capital sigma that you see right here, that's the uppercase. Here's the lowercase sigma. There's the uppercase. We're going to use the uppercase to stand for sum of a bunch of things. So in other words, the sigma stands for add them all up. So we're going to add them up. So if we say we have our sigma here, we have our index variable, or our counting variable here. A lot of times I'll use k, sometimes I or j are often used for index variables. So you have k equals 1 to n of a sub k. So a sub k is the kth term of some sequence. And so your sequence goes a1, a2, a3, up to an. That's a finite sequence. And then this says add those things up. So if the formula for a sub k is k squared, and we're going to sum that from k equals 1 to 4, we would read this as the second example here as the summation from k equals 1 to 4 of k squared. So what you do is you just take the bottom number where k equals 1 and plug that in. That's 1 squared, which is 1. Then you've got k increased by 1 to 2, so you got 2 squared, which is 4. And then k increases 1 more to 3, so you got 3 in place of k, so that's 3 squared, which is 9. And then you do it again, 4 for k. K squared is 4 squared, which is 16. And we stop there because that's our top number. So the first one number we put in will be our bottom number. The top number will be the last number we put in, and we put in all integers in between there. You can even have some of these things start at 0 or even at a negative integer, but they should be integer values here. So then what do we do with these 1 squared, 2 squared, 3 squared, 4 squared? We evaluate them independently and then just add them up. So 1 plus 4 plus 9 plus 16 is 30. So that's just a shorthand for add up these 4 things. Now if you only have 4 things, maybe this is not such of a big help. But what if you had 4,000 things, or 4 million things, or even 400 things? You wouldn't want to actually list them all out. If we could list it in a sort of a pattern form, then this summation notation would be helpful. Or if it's an arbitrary amount that we don't know how much it's going to be. Now we can do a similar thing with multiplication called product notation. So the Greek version of the letter P for product is pi. There's an uppercase pi and a lowercase pi. Of course, you're familiar with lowercase pi. That's the circumference of a circle divided by its diameter. That's a specific number, close to 3.14. That is a specific number. It's an irrational real number. But the uppercase pi we're going to use like the sigma, but this time instead of adding them all up, it's going to be multiply them all together. So the product from k equals 1 to n of a sub k is a1 times a2 times a3 all the way up to a sub n. So the product from k equals 1 to 4 of k squared, again you let k equal 1, 2, 3, and 4, again getting 1 squared, 2 squared, 3 squared, 4 squared, which reduces to 1, 4, 9, and 16. But this time, instead of adding them up, you multiply them. So 1 times 4 times 9 times 16 is 576. And so that's product notation. Now summation notation comes into play because when we're doing a sum like this, what we're doing is we're computing a series, the sum of a series. And notice that the formula here is a linear type formula. By now we should recognize that. That the output is 2 times the input plus 5, or down here 3 times the input minus 2. And so these are arithmetic sequences underneath, but the first one is the sum and the next one's a product. So the first one's actually a series, the second one's not, it's a product. But go ahead and figure these out. They only have 5 or 4 terms, so you should be able to figure each term out and work this out. Go ahead and do this now and come back when you've got it figured out. Press pause now. So, of course, what we do is plug in k equals 1 into the formula. In the first example, we get 2 times 1 plus 5 reduces to 7. Then we plug in k equals 2. 2 times 2 plus 5 reduces to 9. And so forth all the way up to 2 times 5 plus 5 is 15. Or, of course, we know we could also figure out these numbers by our pattern that we know for arithmetic sequences. And that is, we start with k equals 1, we get 2 times 1 plus 5 is 7, and then notice that the slope is 2, so we're going up by 2. So that goes 7, 9, 11, 13, 15, for a total of 5 different numbers for k going 1 to 5. So either way you do it, you get 7, 9, 11, 13, and 15, and you want to add them all together, which I believe is 55. Similarly, we can do the one below. This is a product notation. When you plug in k as 1, you get 3 times 1 minus 2 is 1. Plug in k as 2, you get 3 times 2 minus 2 is 4. 3 times 3 minus 2 is 7, and 3 times 4 minus 2 is 10. And of course, here you notice once we start with 1, we're going up by 3, so 1, 4, 7, 10, for a total of 4 numbers. But this time, instead of adding them, we're multiplying them. So the first example was actually a series. This example is not. We multiply them together, we get 280. Alright, here's a problem for you. Write the sum of the first 100 even natural numbers using summation notation. You know, there's a legend that goes with a problem like this one, is that there was a little boy named Carl that was in kindergarten or first grade, something like that, and his teacher wanted to give him, his class, some busy work. So they gave them a problem something like this. Write the sum of the first 100 even natural numbers, not using summation notation, but to actually figure it out, what it would be. And so, basically, I think the teacher's idea was just to give them some busy work to keep them out of the teacher's hair. Well, within a matter of a minute or two, Carl came up and gave the teacher the answer, and not only was he right, he basically did it better than anyone else in the class as far as getting the answer right, or even better than the teacher for that matter. So how did Carl come up with such a quick answer? Well, let's first answer this question here about putting this in summation notation. Well, there are 100 numbers, so we should be able to index that from k equals 1 to 100. And it's a sum, so we can use summation notation. And to make it an even number, it needs to be a multiple of 2, so 2 times k. So notice that this is 2 plus 4 plus 6 plus 8 plus 10, all the way up to 200, which is the 100th even number. Now, let's compute this sum. Are you as fast as the kindergartner Carl? Do you have an answer already? Well, here's what Carl noticed. He saw a neat pattern. Okay? Now we could just figure out all 100 numbers and then add them up. Okay? And of course this is a long time ago. Carl didn't have a calculator, so you'd have to do this without a calculator if you want to compete with him, but it'd be nice if we could find a shortcut, and this is what he did. He said, okay, look, if I write it out this way, and then I reverse it, then I notice something interesting. So let's call this sum S. It's 2 plus 4 plus 6 plus 8, and so forth, and the last part of it is the 194, 196, 198, and 200. Now write it backwards, 200 plus 198 plus 196, and work your way down, 8, 6, 4, 2, and now add them up. And if we add them up in pairs from the beginning to the end, look what happens. 2 plus 200, 202. 4 plus 98, hey, 202. 6 plus 196, look at that. Every single one of them is 202. How many terms did we have? We had 100 terms, so you've got 100 202s added together, so that's 100 times 202. So notice we had 100 terms, we added the first and last to get 202, and we have 100 of those. But now that's twice the sum, because we've got the whole sum listed twice. So 2s equals 100 times 202, so s equals 100 over 202, and so of course 202 divided by 2 is 101, times 100 is 10,100. Actually pretty easy way to work this out, and Carl was able to get this really quickly. Now, don't feel ashamed if you think that this kindergarten kid could get this a lot faster than you could, because this is Carl's last name was Gauss. Carl Gauss is probably the greatest mathematician ever lived, certainly in the top 5 or 10 mathematicians of all times. And he was a bit of a child prodigy. He was able to actually correct some of his dad's arithmetic when he was very, very, very young. Okay, so he was very, very bright. Was probably one of the last mathematicians to really completely master pretty much every mathematics that was known at his time. After Gauss, there's just so much mathematics, it's basically impossible for any one person to master all of it. So can we generalize Carl's pattern to an arithmetic series? Alright, so what we're doing is we're summing something that looks like m times k minus 1 plus a1. Remember, that's the formula for an arithmetic series that starts at k equals 1 and goes up to k equals n. And this time we're going to, that's the formula for a sequence, and then we want to sum that up. That makes it a series. So it's basically a1 plus a2 plus so forth. But one way to think of this is, starting from the bottom, the first term is a1. The next term is a1 plus m. The next term is a1 plus 2m. Now if you start at the other end, an is the last term. The term before it is an minus m. It's m less than an. And the term before that is an minus 2m, and so forth. So if we write this forwards and backwards, look what happens. The first term is a1 plus an. The next term, notice the m plus m and the minus m cancel, and we get a1 plus an again. The next two, when we pair them together, one from the third one from the end and the third one from the beginning, we get a1 plus 2m plus an minus 2m. Again, the 2m and the minus 2m cancel, leaving a1 plus an. And this is going to work for every one of them, so every term is a1 plus an. The same thing we found in the sum of the even integers problem. Now remember, when you add all these together, we've listed the sum twice, so this is 2 times the sum, so 2s is this. Now there are actually n is how many terms we have, so there are n of these things, so what we get is 2s is n times a1 plus an, and so now we have a formula s for the sum of the first n terms of an arithmetic series. Take the first term plus the last term times n and divide by 2. Now if you wanted to, you could realize that the nth term is m times n minus 1 plus a1. And if we want to do a little bit of working around with this, we notice that the a1 plus the other a1 makes 2a1. So we could write it as n times parentheses 2a1 plus m times n minus 1 close parentheses, divide by 2. But actually this first version of the formula is the best version to remember. Just remember this. So remember basically Carl's pattern. If you take the first term and the last term and add them together, they're going to be n copies of that, and that's going to be twice the sum, so divide by 2, and that gives you the sum. So this is a nice little pattern, and this allows us, we can use this to quickly find the sum of an arithmetic series. It's a very, very nice little shortcut. So see if you can use that formula now on these examples. Notice that these are all arithmetic series. There are 5 examples for you to work through here, and use the formula to work this out. When you get answers to all 5, come back to the video and we'll check it. Press pause now. Okay, the sum of the first 1,000 natural numbers, k equals 1 to 1,000, and it's just k is the thing there. So in other words, this is one where the first term is 1, the 1,000th term is 1,000, and there are 1,000 terms, and it's going up by 1 each time. So this is in fact a arithmetic series, slope of 1, and so we get our formula is 1,000. That's n times a1 plus an over 2. That's 1,000 times 1 plus 1,000 over 2. That's 1,000 times 1,001 over 2. 1,000 divided by 2 is 5,000. 5,000 times 1,001 is 500,500. And we can write a formula for the sum of the first n natural numbers in terms of n. Is the sum from k equals 1 to n of k. Well, the first number is 1, the last number is n, and there are n of them, and it's over 2. So it's n times n plus 1 over 2. Alright, let's look at the next 3 examples. The sum from k equals 1 to 250 of 3k minus 5. Notice the 3k minus 5 is a linear type or arithmetic type sequence that we're adding up to make an arithmetic series, and the slope is 3. We're adding 3 each time that we go up. So the first term, we could write out a few terms, for example. The first term is 3 times 1 minus 5, that's negative 2, and then we're going up by 3. So it's negative 2, then it's 1, then it's 4, then it's 7, and we're adding all those up. And we end with the last term is when we plug in 250 for k. So the total of from 1 to 250, that's 250 terms, so that's n, that's 250 on the top, 2 on the bottom, and in the parentheses we need to figure the first term and the last term. Well, we figure the first term by plugging in the lowest number, k equals 1. 3 times 1 minus 5 is negative 2. We get the last term by plugging in k equals 250. 3 times 250 is 750 minus 5 is 745. And so we get the first term is negative 2, last term is 745. If you add those, that's 743. And then we multiply that by 250 over 2. 250 over 2 is 125. 125 times 743 is 92,875. Similarly, if we add up from k equals 1 to 201, 2k plus 7, plug in k is 1 to get the first term. That's 2 times 1 plus 7 is 9. That's the first term. The last term is 201. 201th term, k is 201. So 2 times 201 plus 7 is 409. So we add those two and multiply by the number of terms over 2. 9 plus 409 is 418. Divide that by 2 is 209 times the 201 is 42,009. Now the next one I did something interesting. Well, first of all I got a negative slope, but also I've got the k it goes from 4 to 175. But this still is an arithmetic series. We can still use the same formula. So the first term is that we actually have is when k is 4. So plug in 4 to find that. So negative 2 times 4 plus 25, let's see, negative 2 times 4 is negative 16, plus 25 is negative 2 times 4 is 8, plus 25 is 17. Okay, that's good. And then plug in 175 for the last term. Negative 2 times 175, okay, plus 25 is negative 325. Add 17 and negative 325 together, negative 308, divide by 2. But now we have to multiply this by the number of terms. Now this time 175 is not the number of terms because we leave off the one at the bottom. So we're leaving off these 3 terms at the bottom. So the easy way to find the number of terms is take top number minus bottom number plus 1 more. So notice negative 4 plus 1 is negative 3, and that's exactly how many terms we're eliminating at the bottom. So that tells us we have 172 terms. Okay? And so work this out, and you get the sum to be negative 26,488. Alright, here's an application. An auditorium is set up so there are 25 seats on the first row, and each row has 2 more seats than the previous row. There are a total of 103 rows. How many seats are in the auditorium? Okay, I did this in summation notation. You're going up by 2 each time, so that's 2 times k minus 1 plus the initial row, 25. And we're summing from k equals 1 to 103. So the first row has 25. How many does the last row have? Well, 103 minus 1 is 102 times 2, 204 plus 25, 229 in the last row. So first row plus last row times, something's out of whack here. Let's fix this. So this should be 103 rows each time. So that's how many we're adding up. And so let's work this out. That is 100, let's see, 254 divided by 2 is 127. And I'm going to use a calculator here. 13,081 is the correct answer there. Okay, and 13,081, so the auditorium has 13,081 seats. Okay, so after looking at this video, you should be able to understand the difference in sequence and series, understand and apply summation and product notation, and you should memorize this formula. So you should memorize this formula for the sum of a finite arithmetic series and be able to apply it in real-world examples. So now we know a little bit about an arithmetic series.